All right, here we go with our third lesson of trig. Now jumping into 9.7. So now we're going through some of the formulas and identities, things that we gotta be aware of here. So as we talked about in the last lesson, the inverse of sine is cosecant. So one way to write that would be that cosecant of the angle is the same as 1 over sine, right? Because those are inverses of each other. Just like secant would be 1 over cosine, and cotangent would be 1 over tangent. So that's just the inverse relationship that we've already talked about. We also took a look at tangent being y over x. Remember that our sine value represents the y coordinate. Our cosine represents the x coordinate. So since tangent is y over x, that's the same thing as saying sine over cosine. And then cotangent would just be the inverse of that. So if we were doing cotangent, instead of sine over cosine, it would just be cosine over sine. So those are the most basic ones we need to know. Here's what we call our Pythagorean identities, simply because you think of like a squared plus b squared equals c squared. That's exactly where this comes from. So in our unit circle, let me draw it up here real quick. So one of the things that we took a look at, so if I had a point, so let's just say here's our radius. Remember, in the unit circle, the radius is 1. And so to get to that point, I would have to go over some amount, and then I would have to go up some amount. So it would look like this. And so basic Pythagorean theorem on this would say that x squared, remember that's our cosine. So x squared plus y squared equals 1 squared, which is 1. Since x is our cosine value, we can say that it is cosine squared plus sine squared equals 1. And so that's where this comes from, just a basic Pythagorean theorem process. If I were to take these values, sine squared plus cosine squared equals 1, if I were to, let me do this over here off to the side, if I were to take this, so sine squared plus cosine squared equals 1. If I were to divide everything in that equation by sine squared, it gives us another identity. So I'm going to divide everything by sine squared. So it looks like this. So when I simplify this, well, sine squared over sine squared is obviously 1. Up above, we said cosine squared over sine squared, that's this model, would be cotangent squared. And right up above over here, we said 1 over sine is the same thing as cosecant. So 1 over sine squared would be cosecant squared. And so by dividing each one of those guys by sine squared, I get a new identity. And so that's the one that you're seeing right here. If I were to go back and divide each one of these by cosine squared and simplified it, I would get this identity. And so those are all stemming from this same concept. So that's why they're all called our Pythagorean identities. A cofunction identity simply tells you two angles that add to 90 degrees. So I'll show you really quick with this. So one thing that we've seen on our unit circle is if I were to go 30 degrees, what are the coordinates at 30 degrees? So we looked at this. Our x coordinate would be square root of 3 over 2. The y coordinate would be 1/2. If we were to go 60 degrees, those guys flip. So right here I'm looking at a 60-degree angle. My x coordinate becomes 1/2. My y coordinate becomes rad 3 over 2. And so what I wanted to show you on this is you'll notice that at 30 degrees, my cosine value is rad 3 over 2. Well, at 60 degrees, it's my sine value that's rad 3 over 2. And if you look at what these guys add up to, right, they add up to 90 degrees, right? They're complementary angles. So when you have complementary angles, these guys become equal to each other. So at 30 degrees and at 60 degrees, these two guys would equal each other. So you could do the same thing with your y coordinate. We would say the sine at 30 degrees is 1/2, and the cosine at 60 degrees is 1/2. So when the angles add to 90 degrees, the sine and the cosine value equal each other at those angles. So another way to write that would be to take it away from 90. You'll notice obviously that 60 degrees would be the same thing as 90 minus 30. All right, that still means 60 degrees. So that's just another way of representing these guys as complementary angles because they add to 90. Remember, pi over 2 is just in radians, it's the same thing as 90 degrees. So in other words, they're trying to tell you that sine and cosine are equal when they are complementary, when they add to 90. Right? And so you can say the same thing with this one would mean the same thing. The same thing works with tangent and the inverse of tangent, which is cotangent. Right? These guys are equal when the angles add to 90 degrees. So in other words, all right, just to give you something with some real numbers in it. So if I said the tangent at 30 degrees would have to equal the cotangent at 60 degrees. Right? So their angles add to 90, which was what would make them angle at that point, which would what make them equal at that point. And then the last one here is negative identities. The sine, because sine works up and down, when I travel, see if I have a little space to write it down here. So here's my unit circle. So if I were to go up 30 degrees, you'll notice my sine value is 1/2. If I were to travel negative 30 degrees, so if I were to go this direction, well, my sine value would be negative 1/2. Because sine values represent a y coordinate, right? This is like traveling up, it's positive, and if I travel down, it's negative. So my sine values do change, positive or negative, depending on which direction I travel. So if I go up, it's positive. If I go down, it's negative. The same thing would be true for tangent. So these guys are the same rule, that the sign does change when you travel in the negative direction. However, with cosine, it does not change. Cosine works left and right instead of up and down. So if I go 30 degrees, positive 30 degrees, I know my cosine is square root of 3 over 2. Well, if I go negative 30 degrees, my cosine value is still positive 3 over 2, square root of 3 over 2. Right? The sign doesn't change because cosine doesn't work up and down like sine does. Cosine works left and right. So my cosine is only affected if I go over to here. Right? But as I travel to the right, because both of these guys are traveling to the right, even though one's above the x-axis and one's below it, they both still went to the right. And so because you're going to the right, they both remain positive. So cosine is unaffected, right? The sign would remain positive even when I travel in the negative direction. So that's what those guys are telling you. So let's look at a couple examples here. So looking for all of our trig functions. So we are told here that the sine of an angle is 1 over 5. And what this is telling you is which quadrant should you draw that in. So where are we between pi and pi over 2? So remember for this guy, let me put this one off. I'll put it right here in the middle so we can kind of keep it on the screen. So remember in your circle here, this is pi over 2. We know this is pi. This is 3 pi over 2. And this would be either starting at 0 or if you go all the way around, you're at 2 pi. So that's what separates our quadrants. So if I am between pi and pi over 2, what quadrant would that put us in? Right? So we know that would have to be in our second quadrant. So when I go to draw this triangle, this simply tells me what quadrant I should be drawing that in. So it's quadrant 2, so I'm going to draw my triangle here in quadrant 2. And I always want to connect my triangles to the x-axis. Remember that sine, if you go back to your SOHCAHTOA phrase, sine is opposite over hypotenuse. So opposite over hypotenuse. So this is our reference angle. In order to get the third value, we would just do a little Pythagorean theorem. So 1 squared plus b squared equals 5 squared. So if we did that, I'll only write it out for this one here. Oops, plus b squared equals 5 squared. So if you looked at this, this is 25. I'm going to subtract the 1 and I'm going to get 24. And then I'll have to square root it to get b by itself. So it becomes the square root of 24, which, you know, we can write it as the square root of 24. You could simplify that to 2 radical 6. And so that's always good to simplify your radicals as well. But just for the sake of an example here, let me go from here. So now when they say, what are the other 5 trig functions for this? Well, now that I have this, it'll be really easy to identify what are the other trig functions. So just like we've done before, I have my sine, cosine, tangent, and then I have their reciprocal functions, or their inverses. So the inverse of sine we know is cosecant, inverse of cosine is secant, inverse of tangent is cotangent. So those are the 6 functions. They gave us 1 to start with. That's our 1/5. That's our sine value. And remember, right off the bat, cosecant is just going to flip that guy upside down. So I know 5 over 1, or 5, would be my cosecant value. Cosine, we do adjacent over hypotenuse. So rad 24 over 5. And again, I would flip that upside down to get my secant value. So it becomes 5 over 24. And yes, typically we don't leave the radical on bottom. So we do rationalize our denominator by multiplying by itself. Right, so we can do that to rationalize the denominator and not keep the radical on bottom. I'll do that with another one here in just a second. For cotangent and tangent, again, tangent is opposite over adjacent, so 1 over root 24. And same drill, I could rationalize my denominator. If I flip that upside down, I just get the root of 24 for my cotangent. So let me jump over to one more. Let's see, so cosine would be not too different from this one. Let me go with something that'll put us in a different quadrant here. One thing we needed to mention on number 1 is the issue of the signs. Remember, anything that travels left or down should be negative. So that would make this guy negative. So I should have put a negative on my square root 24 setups. All those guys should come out to be negative. So let me do another one that can involve a negative here. So that would be in quadrant 3. So that might be a good one to do. This would be in quadrant 4. So let's take a look at this one. I'm trying to give you one that I think would be a little bit tougher. So I'm going to go to quadrant 4 here. So between this guy and this guy, we know is in quadrant 4. So when I draw this, try to give myself a little more room on this one. So I'm going to draw it in quadrant 4. Remember that you always connect a triangle with your x-axis. So it's going to look like this. Secant is the inverse of cosine. Since cosine is adjacent over hypotenuse, secant would be hypotenuse over adjacent. So in this case, I am given the hypotenuse over the adjacent leg. So it's going to look like this. And again, I'm going to do a little Pythagorean theorem to come up with my missing piece here. So if I did something like 3 squared plus b squared equals rad 13 squared. Of course, the square root of 13 squared is just 13. So if I subtract over the 9, now I have 4. And if I square root that 4, I get 2. And then obviously super important that we keep track of what our signs would be. So anything that travels left or down is negative. So I know this guy would be negative. Your hypotenuse is never negative. It's only the 2 legs that could create that negative value. So again, we're right back into sine, cosine, tangent, cosecant, secant, and cotangent. So those are the 6 functions that we're always looking for. They gave us 1 to start with, the rad 13 over 3 for secant, So I would flip that upside down to get my cosine value. So let me work out a little side work here. If I flip that upside down, it does put my radical on bottom. So we're going to do a little side work to clear that. This is what we call rationalizing the denominator. If I multiply straight across, I get 3 root 13 over 13. And so this would be the more appropriate way to write our cosine value. So 3 root 13 all over 13. So if you can ever reduce these two, you're allowed to do that. So that's always a good thing to do. Obviously, we cannot in this case, nor can I simplify the square root of 13. So I'm going to have to leave it like that. So we got 2 out of the 6. So let's come up with the other ones. Sine we know is opposite over hypotenuse. So negative 2 over rad 13. Again, if I multiply this by square root 13 over 13, I can rationalize my denominator and give it a more appropriate answer where we don't leave the radical on bottom. So for sine, we're going to call that negative 2 rad 13 over 13. I'm going to run out of room here, so sorry, I got to write this kind of small. Again, if I flip this upside down, I get my cosecant value. And I don't want to do that from here, I want to do that from here. Right? So cosecant, if I flip this upside down, is simply rad 13 over negative 2. So it can look like this. For tangent, let's get our final two here. Tangent, we are doing, oh, these will be nice and friendly. So opposite over adjacent, so negative 2 over 3. And if I flip that upside down, I get my cotangent. So these, again, will just tell you what quadrant to draw your triangle in. Make sure you get the appropriate signs in there. And then we're just using those guys with SOHCAHTOA to find the remaining trig functions. All right, so simplifying this will all come back to those identities that we just looked at on the previous page. If I wanted to simplify something like this, one thing you could do is separate these guys. So I'm going to write this as negative 1 over secant times tangent. So I'm just separating out those two functions. Notice it's still tangent over secant, right? The same as this would be. My secant's still on bottom, my tangent's still on top. But you'll see why we separated that. Secant, we know, is the inverse of cosine. So I can actually bring up that function by changing it to cosine. Tangent, we know, is sine over cosine. And now we can see what would cancel, would be those guys right there. And I'm simply left with a negative sign. Jump over to this guy. So again, we talked about this on the last page, complement angles. So the complement angle of cosine we showed on the last page is sine. So I know that this guy, it would equal our sine value at the angle. 1 minus cosine squared. So remember, we looked at this as well. One of our Pythagorean theorem identities is that sine squared plus cosine squared equals 1. And one thing you're always allowed to do with any formula is to rewrite it. So I can subtract this guy over to the other side. So if I subtract over my cosine squared, I can rewrite it to look like this. So you'll notice right here, 1 minus cosine squared is equal to sine squared. And so now I could actually combine these guys together and just call it sine to the third of theta for that. One thing you can keep in mind with all these, the ones with exponents on them, is they tend to write it here. That's just a notation thing. The sine cubed of theta is the exact same thing as writing it this way. Right? Those two things mean the same thing. This is just the more common way of writing it. Let me give you a couple more examples here to close it out. Again, with some of the more complicated ones, just in the interest of time, let me work through just this one right here. We did look at a couple other Pythagorean theorem identities back there. And one of those was that secant squared is equal to 1 plus tangent squared. So I can replace my secant squared with 1 plus tangent squared. And I'm just going to rewrite the rest of it here real quick. One of the other things we can notice is we saw these guys on the other page as well towards the bottom, that the tangent of a negative angle is the same thing as the tangent of x. And so those signs did change places. Let me just show that to you really quick so you remember what I'm talking about. So that was these guys right here. Right? So the tangent of the negative angle becomes negative tangent theta. Right? And so we get that one right here. So we talked about how sine and tangent both do that. And cosine, it does not, right? It stays the positive angle. So we can replace this guy with negative tangent. Go back to these. So this can be replaced with negative tangent of x. And this guy, as we showed, is unchanged by the negative angle, can just be written as cosine of x. So now we have everything in terms of just positive x, which is one of the things we were hoping here so we could combine things together. Let me do a little distribution on top. So 2 plus 2 tangent squared x minus 2 tangent squared x. Hopefully you're seeing something right there. I'll keep my denominator as it is for now. So negative tangent of x times cosine of x. So you can see right here, these guys would obviously cancel out. So a positive 2 tangent squared minus 2 tangent squared would cancel. So we can do that. Remember that, so I just have the 2 on top right now. Remember that tangent is the same thing as sine over cosine. And so on bottom, my cosines cancel. And so all I'm left with is a 2 on top and a negative sign on bottom. So let me write it this way. And so the one last thing we could do is, remember, the inverse of sine is cosecant. So if I want to bring that up top, I could write it this way. And that would be our answer. So some of these, it's just a matter of looking back at those identities and formulas and just substituting so that we can find things that would cancel and simplify. So let me take you down to this last portion, which is verifying an identity. All that means is we need to take one side of this and make it look like the other side. As a general rule of thumb, when you verify an identity, we are looking to pick the side that looks more complex and simplify it to look like the side that is simpler. So we want to go from complex to simple. So which one of these would we say looks more complex than the other? So I would probably say that left side looks more complex than this one. So let's see if we can simplify this to make it look like negative sine to the fourth. So one of the things we already looked at is 1 minus cosine squared is sine squared over secant squared minus sine squared. So we're just bringing this guy down all the way. We're not touching the right side here. Secant squared, remember, is the inverse of cosine squared. So we can move this guy to the top by changing it to cosine squared. So I'm looking at sine squared theta times cosine squared theta minus sine squared theta. And so one of the things we could do at this point is we can factor out the greatest common factor. So I'm going to pull out sine squared theta as a common factor. That's going to leave me with cosine squared minus 1. And remember, you can always, when you're checking factoring, if I were to distribute that, you can notice that it would give me back what I started with. So I know I'm good to go. And again, cosine squared minus 1. Whenever you want to change the signs on this, because cosine squared minus 1 isn't really the formula, 1 minus cosine squared is. And so I really want this to be the negative and my 1 to be the positive. And so I need to be able to change my signs. So one of the other things we could do on this is factor out negative 1. So by pulling out the negative, it allows me to switch the order of what I have. So now it looks like this, right? So this negative, remember, if I distribute, my 1 becomes negative, which gives me this guy. And if I multiply these together, it becomes positive, which gives me this guy. So I didn't change the value of anything, but by pulling out the negative, it allowed me to flip the order of what I have. So now it fits a formula. We know that 1 minus cosine squared is sine squared. And so now when I multiply those guys together, I'm creating that negative sign to the fourth. And we were able to prove that it does equal that right side. So I know these guys can be a little tricky, and it can be tough to see the right path on these. But again, a lot of it's just a matter of connecting it to a formula and being able to substitute so that we can simplify on those.